we're going to take a look at Chapter 10, which is going to cover the basic ideas of probability. This video is going to help you compute theoretical and empirical probabilities. So first, there are some key terms we need to discuss, such as probability experiments. In a probability experiment, we are trying to examine if our hypothesis is correct and understand what's happening from a probability perspective. And what the outcome from that investigation is called results or an outcome. An outcome would be the results of one single trial. So if I flip a coin and I get heads, then that's one trial. If I am trying to test crashing an item and I crash it once, then that's going to be one probability event. So we're not doing things multiple times. So how can I find probability from a percent chance? So when I flip a coin, what's the chance that I'm going to get heads? Most of us are pretty familiar with that problem. We know that there's a 50% chance that I'm going to get heads. And so if there's a 50% chance, that's coming from the fact that there's two possible outcomes and getting heads is one of the two. So 1 divided by 2 is 0.5. And then to get from 0.5 to the percent, I have to multiply by 100. So when we're working with probabilities, it's going to be important to remember to multiply by 100. A sample space is going to be what the outcomes are. So if I flip a coin, my outcomes are heads or tails. If I roll a die, my outcomes are 1, 2, 3, 4, 5, 6, assuming it's a standard die. If I'm doing a true or false question, there's two outcomes, true or false. And if I'm flipping two coins, then I have 4 possible outcomes if I'm flipping two at the same time. When we're working with probability, we use the term event to stand for a subset of the probability experiment. So if I have a deck of cards and I draw a card, that is the experiment. There are 52 outcomes in a deck of cards, so that's my sample space. And then the event would be that I drew an ace. So it's a specific what happened when you drew, what happened when you flipped the coin, what was the outcome. And so the way to think about theoretical probability is the number of outcomes that will get your goal event divided by the total number of outcomes. So here are some examples where we can talk through. I'm rolling a single die, and you want to calculate the probability for A, B, and C. If I'm wanting to roll a die and get a 5, there's only one way to get a 5. I have to actually roll the number 5. So that's 1, and there are 6 numbers on a die, so it's 1 out of 6. If I want a number less than 5, then that means I have 1, 2, 3, and 4 are all less than 5. And so that's 4 ways I can roll a number less than 5. So that gives me 4 divided by the 6 total options, which reduces to 2/3. In part C, there are 3 possible outcomes to get an odd number. I could roll a 1, a 3, or a 5. So there are 3 ways to get what I want, and there are 6 total outcomes, which is going to be 3 divided by 6, and that reduces to 1/2. Let's look at a few more examples of this so we can get to where we want to go. So here I'm flipping 2 coins. So imagine I'm flipping 1 on each hand, and I want to find the probability of getting 2 heads. So if I want to get 2 heads, that means there's only one way to get that. I have to get heads on both coins. So it's not 2, it's because it's one outcome where heads is on both coins. There are 4 possible outcomes because I could get heads and heads, heads and tails, tails and heads, or tails and tails, which is where the 1/4 comes from. If I want at least one head, that would be heads and heads, heads and tails, or tails and heads. So that's 3 possible ways that one of my coins can have a heads on it. And there were 4 total outcomes, which gives me 3/4. If I say at most one head, that is a similar situation where I just want to have one head. So that's ruling out the heads and heads scenario, But if I say at most one heads, that also includes tails and tails because I want no more than one head, and tails doesn't have any heads, so it falls into that category, and that's why we have 3 over 4. A few facts about probability. Probability is never going to be negative. It's always going to be a positive number. It's never going to be greater than 1 or 100% because I can't have over 100% chance of something happening. When an event can't possibly occur, the probability is 0. So, for instance, if I ask you what are the odds of rolling a 10 on a die, I can't roll a 10 on one singular die, so the probability is going to be 0 because that's an impossible event. If you add the probabilities for every outcome in the sample space, it's always going to add up to 1 because I have to get to that 100%. So if I think about it, what's the probability of flipping a heads and a tails on a coin? That's 50% plus 50%, which is 100%. So when you're adding up all of those probabilities, they're going to sum to 1. So if I want to look at a complement of it, in a complement, it's a little bit like an opposite. So it would be, what's the chance of not getting heads? That would be a complement to flipping heads. So it's basically putting a not in front of it. And what we do there is we just do 1 minus the probability of getting heads, or 1 minus the probability of getting a 5 on a die. So in this example, we have 32 trials in a country court. 5 are homicides, 12 drug offenses, and 6 assaults, and 9 property crimes. If jurors are assigned randomly, what's the probability that a given juror won't get a homicide case? So there are a couple of ways we could do this. We could do this by finding the probability of getting any case but a homicide case. Or we could find the probability of getting a homicide case and then subtracting that probability from 1. So if I want to walk through the first way, I'm going to look at what are all the cases that are not a homicide. So I'm going to add those up. So there's 12 drug, 6 assaults, and 9 property crimes. So that means 12 plus 6 plus 9 is 27. So there are 27 cases they could get assigned to that are not a homicide. Then there are 32 total cases. So finding the probability this way, I get 27 over 32. If I want to go the opposite way, I could say there are 5 homicide cases. And so if I'm working with 5 homicide cases, the probability of getting a homicide is 5 over 32. Then I could say the probability of not, which is the complement, getting a homicide is 1 minus 5 over 32, and that gives me 27 over 32. So those are 2 different ways to calculate it. Depending on the problem, it may be easier to use one or the other. Empirical probability is really interesting. It's observed answers. So just because the chance of getting heads on a coin is 50% doesn't mean that if I flip a coin 10 times, I'm going to get 5 heads, because real life happens. There's friction, how high you toss it, there's variation in coins, there's a lot of things in play. And so empirical probability is actually doing it and saying, this is how many times I got heads divided by this is how many times I flipped my coin. So this is going to be a bit of a long example, but it's not going to be complicated. So I have 500 people in the sample. 210 have type O, 223 have type A, 51 have type B, and 16 have type AB. So if I want to set up a frequency distribution, I can use those numbers to do that. So in part A, they're asking, what's the probability that a patient can only receive only one type of blood? So if I look at the frequency and I kind of make a chart here, it makes it easier for me to reference back so that I know what my numbers are. The only group that can receive one type is type O. People who are type O have to get type O. So I'm going to go into my chart and figure out how many people are type O, which is 210. I'm going to divide it by my total, which is 500. And then when I do 210 divided by 500, I get 0.42 or 42%. So 42% of people require only one type of blood. In part B, a patient with type B can receive either O or B because O is a universal donor. So if I want to know O or type B, I'm going to add 210 plus 51. So there are 261 people that could donate to somebody with type B, and there are 500 people total, which gives me 0.522 or 52.2%. In part C, I'm looking at what's compatible with A. And so type A can get either A or O. So my type A blood is 223 people. I have 210 O's, so I add those together to get 433 donors. If the donor isn't from A, then they must be from O, which is a frequency of 210. So that gives me 210 divided by the total, which has been changed because I'm looking at A or O, which is 433, which gives me roughly 48.5%. In part D, there's only one group whose blood can be donated to one type, which is going to be type AB. So the question is really asking us to find the probability of a random donor not belonging to type AB. And so this is a situation where it's easier to do the 1 minus. So I have 16 people that are type AB. So if I do 1 minus that, that gives me the probability of who is not type AB, which is 96.8%.